Thank you very much. I hope I'm going to make it worth you getting up early this morning. I appreciate everyone being here. Can we turn the lights down a little bit, or is that not possible? Terrific. Okay. So what I'm going to do is take you out of Stockholm, around the Earth, around the solar system, around the universe, and back in 40 minutes. So let's go from here. So it's easy to imagine that the very first science was astronomy, because our ancestors must have looked up. And we know they did, and they looked at the stars and wondered, is it possible that there are planets or other creatures on these stars, on these planets around the stars? But this is really the first time that we've been able to ask these questions and come up with an answer that is perhaps scientific. And the reason for that is that we have an enormous number of space missions going out both within our own solar system, but also looking outward. We saw some of the pictures yesterday from Hubble and so on. We also have discovered an enormous number of extrasolar planets, and we'll get back to that a little bit later in the talk. And so, whereas before the only places that we knew for a fact there were planets were in our own solar system, but we now know for a fact that there are many, many more. It used to be, first it was 1, and then 2, and then 5, and now they're just coming down so quickly, you have to sort of keep track each day for how many planets and planet candidates there are. The fields of molecular evolution and now synthetic biology have had enormous impact on the field. So even when I was in graduate school, you'd sit around discussing protistan evolution, and you'd say, well, maybe this dinoflagellate's related to ciliates on the basis of looking at the flagellar ultrastructure and so on. But these evenings would always end up with, but unfortunately we'll never know. But now we do know, and that's what's so remarkable. In a very short period of time, we have the tools to really go down and understand evolution at a really gut molecular level. And then finally, we know an enormous amount about life in extreme environments. This is something that was almost unknown 30 or 40 years ago, and I'm really privileged to be speaking in the same session with Carl Stetter, who is certainly one of the founders of the field, along with Tom Brock, many others who had the courage to go to some of these environments that everyone else said were completely sterile, and discover not just life hanging on there, but thriving in high salt, high temperature, low temperature, high pH, low pH, and so on. And so all these things together mean that we can now start to look at this question of whether we're alone in the universe in a very scientific way. So how do you go about doing this? So I'm going to try to boil this down into 4 simple steps to look for life in the universe. First, you have to know what you're looking for. That's sort of a no-brainer. And we do that by looking at the one place where we know that there is life, and that, of course, is planet Earth. The second thing is to understand what the limits are for life on the Earth. And what this does is it gives us a minimum envelope for looking for life elsewhere. So if we know that life can survive in a boiling acid spring, basically boiling battery acid on the Earth, it doesn't mean that this particular organism will be found on Venus, but it means that it's at least worth looking at a place that also has boiling battery acid. So it's a minimum envelope for life. So it's a place at least to start. And so once you've gotten that part, you know what you're looking for and what the minimum envelope is for life, then you go back out from planet Earth and try to understand where there might be habitable environments that these organisms could map onto. And there's Enceladus. And then the final thing that we started doing in our lab is saying, okay, we found this place that's great. There's nothing on Earth that can survive there. Is it because maybe it simply hasn't evolved, or it's gone extinct, or we simply haven't found it, or maybe it's that life cannot actually live in this environment? So let's go back to the lab and try to make an organism that can live in that environment. And so this is basically the outline of what I'm going to be talking about today. So how do we know what to look for? Now, we could easily spend the next hour or days talking about the definition of life. And there are many of them out there. Many of them are actually sort of a laundry list of the characteristics of life on the Earth. And so it's really more descriptive rather than an actual definition. And so as a biologist, perhaps it's a little bit embarrassing to keep going back to Schrödinger and talk about living organisms as anti-entropy machines. So all of us in this room, I think, are full grown, and I'm sure you're well aware of the fact that we eat to fight entropy, certainly not to grow any taller and hopefully not to grow any fatter. So, I mean, this is something that we're concerned with at least 3 times a day, fighting entropy. But beyond that, I'm trying to look for maybe universal aspects of life. So not just ones that you would find on the Earth, not a very Earth-centric, but a universal sort of definition. And the first thing that I would argue that we have to look for is life based on carbon, organic carbon in particular, and along with that comes hydrogen, nitrogen, oxygen, phosphorus, sulfur, and I think increasingly metals. Thank you, Bob. Now, the periodic table is somewhat overwhelming to the average biologist, but this is an astronomer's view of the periodic table. I wish I had known this before I took chemistry. I might have become an astronomer. It's so much simpler. And what we're showing here are the cosmic abundances of various elements. So you can see that virtually everything is hydrogen, 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 and then helium. In spite of Congress making laws about our national helium reserve, there is actually a fair amount of helium in the universe. And then after that, you see these elements that are so important for life: carbon, nitrogen, oxygen, phosphorus, sulfur, there's magnesium, and there's carbon. So why do I argue that carbon is sort of the non-negotiable starting point for life? Well, it's the 4th most common element in the universe. So there's lots and lots of it. You can't build life on hydrogen, helium. One could argue we have a lot of friends based on hot air, but in fact, life has got to be carbon, not one of those others. It's capable of forming all sorts of really, really interesting compounds, including very long-chain polymers, such as, for example, proteins and nucleic acids and so on. So it can do all sorts of really interesting chemistry. Silicon can do some interesting chemistry, but not what carbon can do. And then a really interesting point, my colleagues who do interstellar chemistry look out into space and they say that what we find out there actually is organic chemistry. And so what's really scary, and I particularly feel bad looking at the chemists in this room who are far better than I could ever dream of being, that in fact, if there are students on a planet, say around Alpha Centauri, their biochemistry books are in essence like our biochemistry books, except in Alpha Centaurian. There's not anything that's really radically different, and you'll see why I'm arguing that as we go on. So the sort of things that we base life on Earth, amino acids and so on, are actually found out there in the interstellar medium and during laboratory simulations and so on. And finally, I think the real argument against a silicon-based life is that if you're going to have a silicon-based life, I can think of a terrific place for it, and that's what we're sitting on right now, planet Earth. Turns out planet Earth is one giant silicate rock. Sorry, I went a little fast for that. So you can see that silicon's about 28% of the Earth, and carbon is 0.03%. And so this would be a terrific place for silicon-based life. And except for my beloved computer, most life on Earth is based on carbon, not on silicon. In fact, no life on Earth is based on silicon at this point. So I think that carbon is non-negotiable. So once you start with carbon, you need a solvent. Now, I'm not quite as glued to water as perhaps I am to carbon, but water is really a terrific solvent for a lot of reasons. There is an enormous amount of that in the universe, too. You can tell from that astronomer's periodic table there's a lot of hydrogen and a lot of oxygen. It's not at all surprising there's a lot of water in the universe. It also has all sorts of interesting chemical properties, and we could go into bonding and so on. But let me give you 2 that are really, I think, quite interesting. One is that water is unusual in that when it's solid, it's less dense than when it's liquid. And this allows having something like an ice-covered moon, for example, Europa or Enceladus, with then liquid solvent, liquid water underneath the surface. Otherwise, you would have freezing from down below. The other thing is the other potential solvents are liquid at a much lower temperature than water, and so this would be also advantageous for life to be able to access a higher temperature range. There are all sorts of other reasons, but there's some of the big ones. And what do I mean by the fact there's a lot of water out there? Here's an artist's conception of what the area around TW Hydri looks like right now. And you can see that pale blue ring around the outside is water vapor. This is a snapshot of what our early solar system probably looked like before the comets and so on were formed. So an enormous amount of water there ready to condense in with the formation of the solar system. Now, as I said, I'm really bullish on water, but not quite as bullish as carbon. And one of the reasons is that there's this moon of Saturn called Titan. And I've become convinced that God has placed Titan in our solar system to test our faith in liquid water. Now, here is Titan. This is, again, an artist's conception. This is not a photograph, although I'll show you a photograph later. And it doesn't look unlike perhaps the fjords of Norway, except a little bit of strange color. You can see the liquid in the mountains there and so on. The problem is that it's way too cold for liquid water. So that liquid is some combination of ethane, methane, and so on. The rocks there are water, ice. So you have a situation that looks oh so familiar, except that they're the wrong compounds. And so here is a place that actually has much more organic carbon and at least solid water than anywhere else in the solar system, so it would be a perfect place for life, except for the fact that the liquid is not water. The solvent is methane. Now, it's possible that there's liquid water beneath the surface. We don't know yet. Love to have another mission back there. It's going to take a while before we get there again. So I'd leave the jury out, but boy, wouldn't it be great if we could use one of those other compounds as a solvent for life. Now, there are all sorts of other things we could go into. We're going to assume that the laws of chemistry and physics are roughly constant throughout the universe. Natural selection, they say it's not just a good idea, it's the law. You get a selective tyranny of the environment. And what I mean by that is that, for example, organic carbon compounds absorb in the ultraviolet range, so ultraviolet radiation is going to be dangerous to any life form that's based on organic carbon, and so on and so forth. We can argue a lot of these extremes. And you're going to need some source of energy that was mentioned yesterday. Solar radiation is always a great idea if you're in a solar system, but there are certainly other forms of life, and solar radiation has its downside with the UV and so on. And finally, you need a certain amount of time. And you hear people talk about, well, you need millions of years, or this planet hasn't been around long enough because it's only 1 billion years old. So where do these numbers come from? I think they come really as much as anything from our feeling that life must take a long time because life is incredibly complex. There is no such thing as a simple organism. All living organisms are incredibly complex. And so time, maybe if everything was right, it was a 3-day weekend, maybe it was a bank holiday, maybe it was 100 million years. We do know that we started to see evidence of life on Earth almost immediately after the late heavy bombardment ended. It probably started before the late heavy bombardment. So we're talking about fairly soon after the Earth became cool enough for liquid water. We think that life could have arisen, but unfortunately we don't have evidence quite that far back yet. So that's sort of the, what are we looking for? So now let's start with that second question. What do we know about the limits of life on planet Earth? And so to do this, we have to look at what are known as extremophiles. And as I mentioned, they give the minimum envelope for life. These guys are the Olympians of the biological world. So what are extremophiles? Well, I'd heard someone in the hall yesterday say, well, it all very much depends on your perspective. And I don't actually believe that. I think it's much more of something that we can have an objective definition. That an extremophile isn't just an organism that lives in a place that we would consider unpleasant, crawling through a cave or, the bottom of the ocean or whatever. But that the definition of extremophile is very much tied into the physical fact that we're based on organic carbon, and we use water as a solvent. So any extreme that tests our ability to run our operating system to be an organic carbon-based life form using water as a solvent is an extreme environment. So, for example, if your solvent, if your water freezes solid, it's a non-starter. So that becomes an extreme environment. Or if your solvent boils, it becomes an extreme environment, and so on. So what I'll do is give you just the very, very brief sort of tour through these environmental extremes, because if I give you much more than that, we'll just get all hung up with these gorgeous pictures and going around the world, and we won't get to the rest of the talk. So I've done a very awful thing and taken most of those slides out and just limited this to mostly this slide. This is one of our field sites, Lake Bogoria, which is in the Rift Valley in Kenya, which is where the highest pH lakes in the world are found. There are obviously also lots of large charismatic mammals, so it's a fun place to do field work, assuming you don't get eaten by a lion or something. So this particular lake has a high pH, about 9.5, 10. Not the highest in the world, but way up there, and it's a nice picture. It's also high salt, so it's a good place, and obviously high temperature, good place to illustrate some of these extremes. So temperature is the obvious first one. As I said, you have to keep your solvent liquid. So you would imagine that life needs to stay between about 0 and 100 degrees. That being said, there's evidence for organisms that are metabolically active at -5, -10, -15. There are papers out at -20 for microbes that I'm not really sure I believe. Once you have to really squint at the data to see anything much above the baseline. There are reports of the Himalayan midge at -17. And then you stop a moment and you think, Antarctic, penguins, of course, there are plenty of organisms that live well below 0. And so I know, because I've given this talk enough to know that there are people in the audience who are thinking they're cheating. That doesn't count. They have feathers. It's biology. Feathers count. Fat counts. The fact is there are organisms that are plenty metabolically active well below 0. They just simply maintain their internal environment. Similarly, as you go up in temperature, a lot of the eukaryotes, organisms like us, drop out, and eventually you only have bacteria and archaea, and at the very highest temperatures you only have archaea. And I won't say anything more than that because I know Dr. Stetter's going to really focus on that, and he, again, has been one of the pioneers in the field for so many years, so I'll just leave it at that. So the temperature range for life is much broader than what we might imagine just based on what we know about liquid water. pH, same sort of thing. This is going to affect the chemical reactions in your cells. And so you would imagine that you want to stay around pH 7. That's roughly what our cytoplasm is, more or less. That's what we evolved for. We could argue that that's probably what the primitive oceans were like, more or less. But again, although this is a great place to hang out, this is probably what you're drinking for lunch, is around pH 7, that in fact you can go to a much lower pH. There are organisms that have been found at pH 0. I've heard reports of organisms at negative pHs. Go back to freshman chemistry, you can see that actually can be done. The problem has been more getting pH meters to take out in the field that go to -5 or whatever. And you'll hear more about that, I'm sure, in the next few years in the literature. So down to pH 0 and all the way up to pH 10, 11, 12, reports of 12.5. Many of these organisms simply keep the external environment out. And so they, again, like the penguin, keep an internal environment that's much more like we would expect, much closer to neutral, but they're living in an environment that has a much, much broader range of pHs. Desiccation, we use water as a solvent, so the lack of water is obviously going to be an extreme environment, yet there are organisms that can get rid of 75 to 80% of their water, at least during some of their life stages. Salinity, organisms that can actually survive, and we've shown ones that were metabolically active in dry salt. Unbelievable. Not something I recommend, but it is something that's doable. Chemical extremes, these extremes of arsenic, I hate that element sort of is off the table right now at NASA. We don't talk, you don't talk about arsenic in polite society. But there are organisms that live in very high levels of arsenic. Let's just leave it at that. Pressure, mentioned yesterday, organisms that live at very high pressures. Some of them are perfectly happy back out on the surface of the Earth at a normal pressure that we'd expect, and some of them are not. They're specifically adjusted for that kind of pressure regime. Radiation is something that's been near and dear to my heart, has been said, because it's unusual. Unlike these others, it's both an environmental factor, but it's also a mutagen. So it's both parts of the whole Darwinian evolution game. And it is something that, because life is based on organic carbon, every organism is going to be susceptible to. And this one may surprise you, but this is intimately tied into radiation resistance, and that is resistance to oxidative damage. All of us are breathing oxygen in this room, and this is a really good thing. I don't want anyone to stop breathing. The bad news is you're literally playing with fire. You're creating all sorts of reactive oxygen species in your cell, many of them every day, that need to be mopped up. The damage has to be cleaned up. This is a very efficient strategy. It's an incredibly dangerous strategy. And again, don't stop breathing. It's allowed us to be the creatures that we are with the large brains and so on. But it is an extreme environment, I would argue, living in high oxygen. There are many organisms that are perfectly happy and are probably better off because they don't have this oxidative damage, that live in an anaerobic or at least microaerophilic environment. And I always put in electricity because, who wants to live, with an electric eel? This is sort of the tabular version of all that. It was in a paper in Nature a few years ago. So that's really the Cliff Note version of the extremes for life in the universe. But that was all done in a very monotonic way. So what about starting to look at multiple extreme conditions? Because life lives in a multi-dimensional niche space, I like to say. And so, having talked about this for years, we finally got together with some students and have a paper that actually should be coming out this week, according to the website last night, looking at this question of polyextremophiles. The difficulty is that there are many organisms that live in multiple extremes, but short of spending the next 10 or 15 years completely on the road at marvelous field sites, which as I say, it actually sounds very appealing. You do end up having to start by going to the literature, and it's really erratic because people make measurements of different things in different ways, so it's very hard to compare. What is relatively easy to compare is temperature and pH. So we developed a large database of organisms, and I've divided these up so that you can see these archaea that are exquisitely good at living at very high temperature, and you can see them clustered to a large extent at these high temperatures. You can see then the bacteria in blue, and then a few eukaryotes, which tend to live at the lower temperatures in this grand scheme of things. And what's interesting in looking at something like this, and the pictures show examples of those various sort of conditions, is you don't see a lot, for example, acidic, very cold temperature. And so is this a case that we don't have acidic, cold temperature environments on the Earth, or no one's measured them? Or is there something about living in a cold, acidic environment that is difficult or perhaps even impossible for life to do? And that's where the synthetic biology comes in. But I think this is a rather interesting kind of graph because it does show that at least on those two variables, there's an enormous amount of area that's covered, at least by life on Earth. And we can start to then add salinity and so on. And I don't quite know how to envision it, but there's some kind of multidimensional thing out there, and that's what we call the envelope for life. So now we've talked a little bit about what we're looking for, a little bit about the limits for the life on Earth, and I don't know if you can tell behind that text there, I'm holding an evaporite with some organisms in it. There's some cyanobacteria, and then there's some other bacteria in that brownish band. That was up in a salt lake in above the Atacama, actually, in Chile, in the Altiplano. So the next thing is to start to look for other habitable environments that are close by. And what NASA does is say, well, let's follow the water. Now, I've already told you that I'm not quite as enthusiastic about water, but that's not a bad shorthand. There's a good reason to think that we might use water as a solvent. I'm not, as I say, completely convinced that it's required, but it's not a bad thing to go for. So let's start with our solar system. I'm not even going to talk about Mercury. As you probably know, Mercury is closest to the sun. It's pretty much baked dry, and so it's a non-starter for life. At one point, we didn't think that Mercury was rotating, and so one side was always facing the sun, one side was really cold, so I figured there was this thin strip of prime real estate, but it turns out that Mercury does rotate, so darn. So if someone offers you some real estate on Mercury, I wouldn't buy it. So let's now go out to Venus, which is the next planet there, and you may be a little surprised to hear me talk about Venus at all. That's what Venus looks like today. It is literally a hellish place. It has the highest temperature planetary surface in our entire solar system. Actually, it's hotter than Mercury. The pressure is just bone-crunching, 90 atmospheres, say very high temperature, very low pH, high winds, not a pleasant place to live. So you think, why on earth are we even, well, why on Venus are we even talking about Venus? And the answer is that because when Earth arose and Venus arose, they should have been much more similar. The sun was about 25% less luminous than it is today, and the thought is that Venus could have housed liquid water oceans like the Earth does today. The problem is that over time, as the sun warmed, the water vapor created a wet greenhouse effect. So what happened is that the temperature on Venus rose as the liquid water oceans were evaporated into a cloud vapor, and then you end up with a positive feedback effect. And so ultimately you end up with this hellish place that you have today. But there should be a nice water inventory in the clouds. And so at some place up in the clouds, say 50 to 60 kilometers above the surface, Carl Sagan suggested many decades ago that a Venusian life that had started on the surface could have risen up into the clouds. Now, we do know that there are plenty, see, nice place there in the clouds of Venus, if you're planning a vacation. It's one of those places that we could potentially talk about life. The biggest problem is that although we know that there are organisms in our clouds here, and even quite a bit higher up into the atmosphere, no one has actually proven that organisms can complete a life cycle in an aerosol. There's some indicative data from about 20 or 30 years ago, but there's actually no proof. And I'm going to leave you with that thought for about 10 minutes and get back to it. Okay, so we've done Venus, we've done Mercury. Earth, I don't need to convince you that it's infestated with life. I mean, it's a mess. There's life all over the place. So we'll just move on to Mars. Now, Mars is something that, of course, has been deep in our mythos for centuries now, the whole idea that there could have been dying civilizations on Mars and so on. And then NASA, of course, does this bummer of having some missions go up there, and in fact, there are no dying civilizations. What you see are these sort of grainy black and white TV sort of images that were sent down in the 60s, and there's a little bit clearer image from a few years later from Mariner 9, and what you see here is very much what you saw in Laurie's talk yesterday, but much clearer from the Curiosity images, and that is dried stream beds. So there's no evidence of a dying civilization, no evidence of any sort of civilization, but you do see this very stark planet with the dried stream beds, indicating that there had been liquid water much earlier. Now, why does Mars have this problem? Well, Mars is a different situation than Venus. Venus is roughly the same size as the Earth. Mars, you can see, is about half the size of the Earth. There it is, a little red ball towards the front, right beyond Earth. So because it's smaller than Earth, it doesn't have the gravity, and it didn't have the length of tectonic activity that the Earth has had. And so it ultimately lost its atmosphere, and therefore it got colder and colder, and the water froze. So it's not just that Mars is farther away from the sun. That's not the big deal. The big deal is that Mars is smaller than the Earth by quite a bit. And so here you've got Venus on one side of the Earth that became way too hot with the runaway greenhouse, and little Mars on the other side that had the opposite fate, where it lost its atmosphere and got to be very cold. And so that's why people talk about us being in the Goldilocks zone. But again, on early Mars, there should have been the water inventory, there should have been the organics, just like on Earth and Venus and so on in our solar system. So on the right here is pretty much a reasonable sort of map of the history of life on Earth, starting from about, well, there's the formation of the Earth at 4.5 billion years. They say there could have been life back into the Hadean. We have no evidence at this point, but we do starting right after that late heavy bombardment period by about 3.8, 3.9 billion years ago. On the left is a completely fictional, hypothesized account of the history of life on Mars. And what you see there is that liquid water should have been abundant, organic compounds, and so on, during the same time period that life arose on the Earth. And so, again, if we think that life is, well, we know it's possible under those conditions. If it's probable, likely, probable, inevitable perhaps, life should have arisen on Mars at the same time that life arose on the Earth, and then ultimately went into various refugia, maybe the salt crust, maybe the polar ice caps, maybe hydrothermal vents underneath, or perhaps it went extinct altogether. So very interesting possibilities there. So that should have been all she wrote about 30 years ago. And the great thing is that my talk would have been over in record speed 30 years ago. But the problem is that we know much more about our solar system now. And so we can go out beyond Mars to some of these Galilean moons of Jupiter. So here's Europa, which has become very famous in the last few years, because it turns out even though Europa is way farther from the sun than you would expect any reputable place to be able to be and still have liquid water, it turns out it's a moon that's covered with water ice, we believe, with a liquid water ocean underneath the surface. Now, you notice it's pretty dirty, too, and that's not just because, no one's around to sweep it up. It looks discolored because of what we think are organic compounds. So again, these two things should be going off in your head: liquid water and organic compounds, potential for life. And so here's some actual photographs of the surface of Europa that were taken by Galileo. Not Galileo the man, obviously Galileo the mission, and although they were discovered by Galileo the man. So there you have a cutaway of Europa, and there you have a picture of this ice crust. It's very active. You can see changes in the cracks and so on. So here's this place that's got liquid water. Turns out it's because of tidal flexing, of frictional interaction with this enormous home planet, Jupiter, and that allows the liquid water to stay liquid well away from where we would have thought it would be liquid based on its position from the sun. So Europa would be a great thing. Europa is fairly small. I found this image last night. There it is in relation to the British Isles. I couldn't quite figure out at 1 in the morning how to move Europa over so it was right over Sweden, but I'm sure we can handle that for the next talk. Here is, I have to quickly say, an artist's rendition of what it might be like if you could drill through the ice and go beneath the surface in Europa. This is not a photograph, okay? Another warning, this is not a photograph. This is my, wildest dreams. Here's this hydrobot, and it's finding these hydrothermal vents and organisms and so on. And I know that I have a certain number of colleagues who would dearly love to make this a reality, and I'm certainly one of them, and let us hope that it happens. Missions to even go to Europa are on and off the table so fast that I can't be depressed and elated so many times in a week. And even the possibility of landing and then penetrating, seems like it's within grasp, and then it's remote again. So we'll just say that this is a dream at the moment, and let's hope it's a reality in the next few decades. So let's move beyond Jupiter. We could talk a little bit about Ganymede. That's a similar situation to Europa. In fact, I'm getting increasingly excited about Ganymede. But instead, what I'd like to do now is move to Saturn. So you're even further away from the sun. And of course, you have Titan, which we mentioned earlier as this moon that tests our faith in liquid water. This is, again, an artist's rendition of the Huygens probe being released from the Cassini mission in through the atmosphere of Titan. This was in January 2005. And I know that there must be other people in the room who remember this happening. To me, what was incredible is we were getting virtually a live feed from Titan. Now, maybe people the younger people in the room are so jaded and say, oh, of course you get live feeds from Titan. But this is so much farther out than Mars or the moon. I mean, this is way out there. And to get a live feed from Titan, it just blew my mind, I must say. So this is an artist's rendition, as I said, of the Huygens probe dropping. Now, this is an actual photograph that the Huygens probe took as it went through that atmosphere. And what I think is so marvelous is that, again, it looks so familiar. You can see the liquid lake and the stream beds and the mountains and so on. I always joke that it reminds me of landing at Chicago's O'Hare Airport. So I did finally actually take a picture out of a plane, and I've harassed various astronomy departments by turning that into a grainy black and white image, but I wouldn't dream of doing that to you. This is actually a photograph of the surface of Titan. Again, it's so familiar and so remote at the same time. So let's go beyond that and look at this other little tiny moon that suddenly is on everyone's radar screen. And again, for the younger people in the room, this is pronounced Enceladus. It is not pronounced enchilada, or the other dozen things that I've heard it pronounced is actually Enceladus. And it's another little tiny one there. And immediately, this looks familiar. This looks a whole lot like Europa, except you see sort of bluish instead of orangish stripes. Again, the thought is that there's organic carbon in there. There's a liquid water ocean underneath this icy crust. But Enceladus is really cool because it's not just that we hypothesize that there's liquid water beneath it, but we see it. It turns out that there's a geyser coming out towards the bottom, dubbed very cleverly Cold Faithful. And there's a thermal map that I have in the insert there of of Enceladus, and you can see that the water coming out is relatively hot, of course, next to the surface of Enceladus. It's not hot. So this water is shooting out, and then it's freezing and being ripped apart by the high radiation environment. So there's Enceladus, a place that we know has liquid water underneath an icy crust and organics. In fact, there are already publications of the composition of the plume of Enceladus, and it's difficult to read, sort of like an eye chart here, but there are organic compounds in there. So it's not just that we think this smudge is organic and we think that there might be liquid water. We know for a fact there's liquid water. We know for a fact that there are organics up there. So very exciting. Boy, I wish it were a lot closer. Again, that should have been, all she wrote, but now people are talking about Pluto as potentially being ice covered with liquid water. Very iffy, but we'll get a better idea in the next few years when the New Horizons mission gets there. What about beyond Pluto, beyond Neptune? Again, there are all these trans-Neptunian objects that look like they're ice-covered, potentially liquid water. We don't know for sure. We can't completely rule it out. Probably not likely, but I wouldn't have been able to give most of what I told you about in the last 10 minutes 20 years ago. So, I've started in the business not to say it can't happen anymore. So what about beyond our own solar system? I've now given you a whole lot of places just even within our own solar system that life could arise. Well, we're on that as well. As I mentioned, we know something about extrasolar planets, and one of the big reasons we do is this marvelous mission that's coming out of NASA Ames called Kepler. I'm sure everyone in this room has heard of the Kepler mission. We're extremely proud of it. And what this is a satellite that is incredibly stupid, and I mean that in the nicest possible sense. It's brilliant because it is so stupid. All it does is it stares at 150,000 stars constantly, except for when it turns back down and beams the data to Earth every now and again. And what it's looking for is tiny dimmings in the starlight. And when it sees that in a periodic sense, it's indicative that there's a planet. Now, I could show you this chart of all the Kepler candidates that we found and all the confirmed ones, but instead what I wanted to show you is something that I got from the web that's about a year old, but these are all the planetary systems that Kepler had found over a year ago. I'm showing you this because it's such, you could stare at this. It's even more effective when you look at it at midnight, I'll tell you. Anyway, isn't that great? So it's not just planets, these are other solar systems, and this is over a year ago. I couldn't find anything more recent. I suspect it's because it would be so tiny you wouldn't even be able to see it. Yeah, cool is the word for it. Cool. So as of the 27th of May, I'm embarrassed to say I didn't update this last night, but I did update it on Monday night. There were 694 planetary systems, 889 extrasolar planets, and 133 multiple planetary systems out there. So what I did is go to one of these data banks on Monday night and just looked for planets that were between 0.1 and 2 Earth radii, and this is the same data, one's in a histogram form and one's in a scatter plot. And you can see that there are quite a few out there that would be considered in the habitable zone. Particularly, look at that huge clump between about 0.8 or so Earth radii to about 1.5. Why are we so insistent on the radius of the planet? Again, think about the conditions with Venus with a runaway greenhouse versus Mars that was a little bit too small and it lost its atmosphere. If you get too much bigger, you not only have the runaway greenhouse, but eventually you're in the gas giant range. Now, we're leaving out any potentially habitable moons. So potentially there could be some giant planets out there that have habitable moons, and then it's a whole different ballgame. So this, to me is just stunning. This is all stuff in the last couple of years. TESS mission will hopefully go and also get a large number of planets. We're still just looking in our own galaxy. Planets around stellar remnants. Who thought that that was possible? I must say, I had no idea what that even meant a year and a half ago when I got invited to talk at a meeting of planets around stellar remnants. I know a whole lot now more about this. And so basically, once something like our sun goes through a red giant phase, it becomes a white dwarf. The great news is that if you can make it through the red giant phase, you're basically good for forever. I mean, 20, 30 billion years. That's basically forever. So there are, in fact, planets around stellar remnants. The first one was discovered, I believe, around a neutron star 21 years ago, which is why they had the meeting there. So this is a potential area that we have not looked at all. It also gives us a potential way out to make it through the red giant phase. I figure all you have to do is move Earth out far enough, make it through red giant, and then you're good for another 20 billion years. Obviously that's a little bit out in the distance, but for people who like to stay up at night angsting, that's something to think about. So that takes care of the sort of describing life, getting an idea what the fundamentals are, what the limits are here, what we might find within our own solar system and out. But what I'd like to do is finish by saying that the last couple of years we've gotten particularly interested in synthetic biology. As I mentioned yesterday, part of NASA's interest is that we could use that to help aid in human settlement. But what I'm going to focus on right now is using it to help aid our search for life elsewhere in the universe. So we've talked about naturally evolved extremophiles. Why not make ones to fill some of these niches that we haven't been able to find organisms? Now, we could start to fiddle around with definitions of synthetic biology, game-changing discipline, interchangeable parts and so on. But I think at the most fundamental, synthetic biology is very much in parallel with synthetic chemistry. So for millennia, we've done descriptive biology. We've looked at the organisms around us, whether it's with our eyes or with molecular tools or with microscopes or whatever. And now we're actually making new ones. We're doing synthetic biology, making new genes, new metabolic pathways, and I believe ultimately new organisms. And so there are many applications, of course, on the Earth from manufacturing, pharmaceuticals, environmental controls, and so on, and we're saying there's no reason you couldn't take some of those to space. And so some of you are thinking, isn't this unnatural? Is this something that we should be concerned about? And we could certainly argue that this is the way evolution worked in the very early times. There was a lot of exchange of genetic matter, and that in fact, ultimately organisms understood what was self and non-self and ended up with this vertical inheritance, and what we're really doing is just flipping this back to the good old days. That's one argument. Another argument is there are organisms that are swapping around genes to this very day. Here's Galliaria that lives in, well, here's a picture of Nymph Creek in Yellowstone, acidic, high-temperature environment full of red algae. I know they look green, they just don't have red pigments, but they are, in fact, red algae. And this particular alga, it turns out just reported in the last week, has taken a lot of genes from bacteria, viruses, and so on in the environment. So a lot of swapping around of genes. But even more than that, I mean, the fact is that everything you eat, everything you wear, every natural product has been domesticated. Do you barbecue teosinte or do you barbecue corn in the summer? Of course, you barbecue corn. We've already genetically modified teosinte. Do you give your kids wolf cubs or do you give them puppies for Christmas? Of course you give them a puppy. Well, I don't want to give that. We gave our kids ones. No, we didn't actually, but we would have. We wouldn't have given them a wolf. So what we've done in the last few years in my lab is hosted an iGEM team. This is an international genetically engineered machine competition. I know there are some teams in Sweden and so on. It's a worldwide competition. There are over 200 teams this year. But what's marvelous is these teams of extremely bright undergraduates come into your lab and do something over the summer, not write a paper study or think about writing a proposal, but they actually have to get in there and do something because the competition's early in the fall, and of course, everyone wants to do well. So for the last, say, 3 years, 2 years, and now this is my 3rd year, I've been the faculty advisor for the Stanford Brown iGEM team, and here were these excited students last year, getting a little punch-happy by the middle of the summer. This is at NASA Ames with the Google plane in the background. But what they did, and we'll cut to the chase, is one of their 3 projects, they created artificial extremophiles. And this overwhelming list of genes are all the genes that they put in E. coli and were able to show increased resistance to cold, heat, pH, radiation, and desiccation. As I say, I've learned not to tell my students no because they constantly prove me wrong. So in very short order, they were not able to make actual extremophiles, but they were able to push the capabilities of this really boring garden-level organism. Here's an example of some of the data from the desiccation resistance, and there you can see the blue at control and how much more desiccation resistance they were able to get out of E. coli, again, in extremely short order with only a few genes. And so we go back to the Venus Life, which is one of their 2nd projects, and this was, again, very much looking at this artificial extremophile bit, a project that they called Hell Cell, which I think is a marvelous name. And what they did there to get at this question of whether organisms could actually divide in the clouds and aerosols is make a gene for the operon for the ribonucleotase reductase and for the DNA polymerase that had a GFP on it, so they were able to glow. So they're the genes, here are the bacteria with these constructs in them, and here they are glowing, showing the constructs worked. And we were able to show that, therefore, when the organisms divided, they glowed, and so we could actually follow their cell cycle. And so the last bit is to actually do that while they're in an aerosol, and we're negotiating for that. Another person in my lab, is marvelous postdoc, is looking for the most radiation-resistant organisms. He's been to high manganese environments. There are good reasons to think that that's a good place to look. In Chile, in the Atacama Desert, at Moffett Field in California, where we work, mines in Arizona, isolated a lot of organisms that live there. This is a sprinkle plate. You can see lots and lots of pigmented colonies. And already in a year, he's been able to find organisms that are at least, if not more, radiation resistant than Deinococcus radiodurans. I mean, so this is remarkable. So this is just starting to be written up. But you can see Deinococcus is the black line in each case. These are not all bacteria. One of them is a yeast. One of them has viruses. I think it's going to be extremely interesting in the next few years to see what he can pull out. And I must say, it's, you know, in science, we always want to topple the reigning champion on something. And so pleased that we're able to say that we've toppled Deinococcus already. Just some pretty pictures of those organisms. But beyond that, we could even start to think of alternate genetic codes. I've just talked about swapping a few genes. Why not do something even more fundamental, like instead of using GATC, use GATC-ZP, which is what Steve Benner's done, group in Cambridge, the MRC and Phil Holliger's lab, led by Vitor Pinheiro, has made XNAs. That was published in Nature last year. So xenonucleic acids, totally different from the codes that we're using today. So we could do something even more fundamental than that. So I could envision a time where we're making membranes, we're making genomes, maybe we're adding a flagellum, a totally different, perhaps protein system, and literally making new life. And this is something that could be extremely valuable to us because it shouldn't be infective. It could be more efficient at certain things that we need produced, but it can also give us a much better idea of what's possible in the universe. And so along those lines, and I know I'm going to be cut off in just a second, I have another extremely talented postdoc who's been working with me on the potential for not having an RNA world where you have ribonucleotides as sort of the starting point where RNA has been shown to have catalytic activity as well as genetic activity, but say, you know what, if you look back out into space, these interstellar chemists tell us they're amino acids. I told you that at the beginning. Not RNA. You see amino acids, you see the building blocks for proteins, so maybe the universe is trying to tell us something that in fact You start not with an RNA world or even an RNA protein world, but you go straight to a protein world that then picks up RNA. And in fact, note that ribonucleotides are synthesized from amino acids. And again, we could go into much greater detail, but suffice it to say that there is a pecking order for the thermostability of amino acids, and therefore how common they are in things like meteorites, the interstellar medium, and so on. And so this is out of a paper from Higgs and Podrutz a few years ago, and what you can see is that this pecking order includes just a couple that are always on the top, and these are ones that we call the terrific 4. There's also fabulous 4, sorry, and there's also a terrific 10. And so what we're doing is actually making proteins just on using either this 4-letter alphabet of amino acids or the terrific 10, and seeing if we can start to build life that way, because this is what you see. This is what you actually have. These are the raw materials you would have had on the Earth and basically anywhere else. But what if it turns out that we are actually alone in the universe? We won't know that for sure within our lifetimes. We could know that we're not alone within our lifetimes. I don't think we'll give up within our own lifetimes. But if we are, it turns out that everything we think about the origin of life is wrong. That in fact it was a very special thing, and it's much more than simple combinatorial chemistry. And so that will have all sorts of ethical implications. So from there, you really have to end with Darwin, who finishes The Origin of Species by really giving a beautiful astrobiology sentence that's better than, certainly much more poetic than anything you would read today. I'm sure many of you read it. It's grandeur in this view of life, with the several powers having been originally breathed into a few forms or into one, and that whilst this planet has gone on cycling according to fixed laws of gravity. So you're really talking about astrobiology. You're talking about the physical environment interacting with the biological world. But wouldn't it be even more marvelous if it turns out that this is not confined to planet Earth, that in fact you see this all over the place? And so once you go through these steps, knowing what you're looking for the limits, looking for extremophiles elsewhere, and maybe making some of your own, you get this feeling that life may actually be all over the place. And so you have to end with saying ad astra. Thank you.